Hello there. In this video, we are going to discuss detailed solutions of all those questions those are appeared in GATE 2014 set 1 with respect to analog circuit. In GATE 2014, there are 4 sets of questions, out of which we are in the first set. And these are the question number you can find in GATE 2014 set 1 paper with respect to analog circuit. So we will discuss solution detail of each and every question one by one. The first question is question number 9. In this question, you can see one PN diode is given, another one is Schottky diode is given. PN diode has forward drop of 0.7 volt and the Schottky diode has a forward drop of 0.3 volt. We have to find out under this bias condition what is the state of these two diodes, that is D1 and D2. Among these 4 options, which one is correct? So as there are two diodes, basically we have four choices. That is D1 can be off, D2 can be off at the same time, or one can be on, one can be off, or both are on. So we will check by taking one condition at a time, and we will see which one is actually correct. So first take the case when both are off. Let the potential at this point is V1 and at this point is V2. When both are off, if we redraw the circuit for this case, then it will be looking like this, because both are off, so no current is flowing through diode D1 as well as this Schottky diode D2. So it will be looking like this. Hence V1 and V2, we can infer that V1 and V2 voltage is same as the supply voltage, that is 10 volt, because no current is flowing through the circuit as there is no closing of the circuit. So V1 and V2 is 10 volt, but the thing is V1 is greater than 0.7 volt, V2 is greater than 0.3 volt, which means that D1 and D2, which means this supply voltage, that is 10 volt, can make D1 and D2 on. So our assumption of both the diode are off is not true. So this cannot be the case. Let us go to the second case. That is D1 is off and D2 is on. So in this case, if we redraw the circuit, then it can be drawn like this. Because D2 is on, we will replace the diode with a 0.3 voltage source. Now we can find out what is this potential at V1. First of all, we will try to find out what is the current, then we can find out what is V1. So the current is 10 minus 0.3 divided by the total resistance, that is 1.02. That will give us the current of 9.7 by 1.02 milliampere. Now the potential, if we try to find out the potential, V1 equal to 20 into I plus 0.3 volt. So that will approximately give us 0.49 volt. Okay, so V1 is 0.49 volt, and if you see this 0.49 volt is not sufficient to bias this D1 diode, because to bias the D1 diode, that is to forward bias the D1 diode, we require minimum of 0.7 voltage at this node. So as 0.49 volt is less than 0.49 volt, that is V1 is less than 0.7 volt, so D1 cannot be on, so it should be off. So as per the conditions, means it is matching with what we have assumed here. So this condition can be true. Let's check for the other option also. Then the third condition is when D1 is on, D2 is off. So in this case, the circuit will be looking like this: 0.7 volt, and there will be V2. It will be represented as open circuited. But here, if you see, this voltage V2 is same as 0.7 volt, because there is no current flowing through 20 ohm resistor. But this 0.7 volt is much greater than this 0.7 volt is greater than 0.3 volt, that is required to forward bias the D2 diode. Hence D2 cannot be off anymore, it will be forward bias. So our assumption is not true. So means both are contradicting, so this state cannot be the condition. Now suppose both are on. When both are on, we will have this condition like this, that is 0.7 volt will represent the D1 diode, and 0.3 volt will represent the D2 diode. Now we will try to find out what are the current across different branches. Okay, so as V1 is 0.7 volt, we can easily find out what is I2 current. Okay, so I2 current is 0.7 minus 0.3 divided by 20 ohm. That will give us 20 milliampere current. 20 milliampere current. Okay, so this is 20 milliampere current. This is the supply current. This current always has to be greater than this I1, either of this I1 or I2. Okay, so now let us find out what is this I current. I current is nothing but 10 minus 0.7 divided by 1K, that is 9.3 milliampere. This is only 9.3 milliampere and this is 20 milliampere. How this is possible? Because this is not possible, because supply current should be greater than current in either of the branches. So if this is the case, then this I1 current will become in the upward direction rather than in the downward direction, which means it will make the D1 diode off state, that is reverse bias. But we have assumed that both are on condition, so this condition also cannot be true. So that's what I have written here. As the current I is less than I2, I1 will be negative. Negative means it will be in the upward direction, so D1 is off, which is contradicting our assumption that we have taken both diodes are on. So this case is also false. So only one case is true, that is D1 is off and D2 is on. So if you see among the option D, that is D1 is off and D2 is on, is the correct answer. Thank you. Next question is question number 11. In this question we have to find out what is the good characteristic of a current buffer. That is, we have to find out the statement about its input impedance and output impedance. A current buffer, we can say, is a current controlled current source, so with ideally having the property to pass the source current to the load without attenuation. That is the good quality of a current buffer. We can represent the current controlled current source like this. That is, the input resistance is Ri, the current flowing is I. Then this current dependent current source will have A times I. That is, A is the gain and I is the current that is flowing through the input resistance, and this is the output resistance. Now we will connect source and load to it. So if we connect current source and a load, then we will try to find out what is the output current, okay, in terms of input current. So we have connected the current source. Any practical current source will have internal resistance Rs. For a good current buffer, this load current IL that is flowing through RL will be equal to A times the IS, whatever the supply current, means the total supply current will be amplified and it will be supplied to the load. Okay. Now we will see, for this condition to achieve, what are the characteristics of input resistance and output resistance of the current control current source or current buffer. So if we apply the current division rule, we can find out the load current in terms of AI. AI into R0 divided by R0 plus RL, that is the load current. Now we will try to find out what is this current in terms of IS. Okay. So I is equal to IS, that is the supply current, into RS divided by RS plus RI. Now we will substitute these things here. We can get the load current as AIS RS by RS plus RI into R0 divided by RL plus R0. Okay. Now for a good current buffer, we know the condition is the load current will be much closer to the gain times the supply current. Okay. So this factor should be much closer to 1 and this factor should be much closer to 1. For this thing to become 1, this RS value has to be very, very larger than RI. So, or in the other way, if we say, the RI can be very, very less than RS, so that this numerator and denominator can be cancelled. Similarly, in this case also, this RL value should be much less than R0, or R0 value should be much greater than RL value. That means the output resistance must be high, whereas the input resistance must be low. So this is the condition. This factor should be much closer to 1 and this factor should be much closer to 1. For this condition to occur, the Ri value should be much less than Rs and R0 value should be much greater than RL. So the input impedance should be low, whereas the output impedance should be high. So the input impedance should be low and output impedance should be high for a good current buffer case. So if you see among the option, the B is the correct answer, that is low input impedance and high output impedance. Thank you. Next question is question number 12. In this question, a circuit is basically given and there is a feedback thing is given. Okay, IN is the supply input current and RF is the very large resistance connected across the feedback circuit. We have to find out what is the type of feedback. Now to find out the type of feedback, we have to remember certain things or certain rule, you can say. If you remember those things, then you can easily find out what is the type of feedback for a particular circuit or for any particular circuit for that matter. So let us concentrate at the output. If the feedback is taken from the same point, that is where the output is taken, at the same point the feedback is also taken, then that sampling, one thing is sampling, another thing is connection. The sampling will be of voltage type, whereas the connection will be of shunt type. Okay, so this is the thing at the output. Now another point is with respect to output is that that is the opposite to this. If the feedback is taken at different point rather than the same point, at different point the feedback is taken and output is taken at different point. In that case, the sampling will be current and the connection will be series rather than shunt. Okay, so these are the things with respect to the output. Now let us concentrate on at the input. At the input, it will be mixing. Okay, at the output always it will be sampling, whereas at the input it will be always mixing. So if the mixing is happening at the same point, then the mixing is of current type. Okay, mixing is of current type and the connection will be of shunt type. Similarly, this is another point. If the mixing is happening at different point rather than the same point, if the mixing is happening at the different point, then the mixing type is of voltage, whereas the connection will be of series type. So these are the 4 points that we have to remember. Now let us remember a key point. Irrespective at the input or output, if the thing is happening, whatever the thing, that is mixing or sampling, that is happening at the same point, then the connection is always of shunt type. And the opposite is that if the thing is happening at different point, then the connection will be of series type. Now let us consider how to name the feedback. If the feedback name is taken, first thing is sampling at the output it is taken, means either voltage or current is mentioned in the feedback, in the name of the feedback. Then the name order should be like this. First sampling type, that is the output, will be there. Then the connection name can be mentioned, or in the name the mixing type can be mentioned. So it can be of 2 types. The feedback can be written in this way or in this way. That is sampling type at the output, connection at the input, or sampling type at the output with the mixing type at the input. But if the connection is mentioned instead of sampling or mixing, if the connection is mentioned, then the input connection will come at first, then at the second the connection of the output. So in this way also it can be named. So the feedback name can be written in three form: this form, or this form. Coming to our problem, if you see, this is the output and the feedback is also at the same point. So at the output the sampling is happening at the same point. If the sampling is happening at the same point, then the feedback is of voltage type, and the connection will be of shunt type. Now if we concentrate at the input, here is the current, here it is mixing directly to the current, means the mixing is happening also at the same point. Okay, input also the mixing is happening at the same point. If the mixing is happening at the same point, then the mixing type is current and the connection will be shunt type. As per the points I have mentioned in the previous pages, you can easily find out these things. That is what are the things happening at the output and what are the things happening at the input. So if you see in the name, the voltage or current, that is the sampling type is mentioned first. So the output will be mentioned at the first. So the output is mentioned at the first. So the voltage thing will be named. So either B or A can be the answer. Now if you see at the input it can be voltage current or voltage shunt. Voltage current, voltage is mentioned here. So B is the correct answer. So the name can be voltage shunt or voltage current. And if you see among the option B, that is voltage current, is the correct answer. Thank you. Next question is question number 13. In this question, a low pass filter circuit is given, that is active filter using op-amp is given, and also the cutoff frequency of the filter is given to be of 5 kHz. We have to find out what is the R2 resistance value in kilo ohm for this scenario. Now let us find out what is the transfer function, that is Laplace transfer function. V0 by Vi minus Z2 by Z1. Z2 is nothing but parallel combination of these two, that is R2 parallel with 1 by Cs, and the Z1 is simply R1. So after simplifying we will get this. If we represent this in omega domain, or we can find out the magnitude also, that will be coming out R2 by R1 square root of 1 plus R2 square C square omega square. Now we will try to find out now we will try to see how the curve will be, that is at omega tends to 0 what value the h of omega magnitude is approaching, and at omega tends to infinity what value it is approaching. At omega tends to 0, if you see, it is approaching to R2 by R1, and at omega tends to infinity this value is approaching 0. That means at higher frequency the transfer function has the magnitude 0, so it will be acting like a low pass filter. It has a pass band gain of R2 by R1, and it gradually attenuates at higher frequency. Now the cutoff frequency is given here. So the cutoff frequency is nothing but the frequency at which the pass band gain is reduced by √2 times. Okay, so this cutoff frequency is given here. We have given with the cutoff frequency value, that is 5 kHz. Now to get the cutoff frequency expression, we have to equate this h of omega c equal to, we have to equate to this value with equal to R2 by R1 divided by √2. So if we equate these things, we will get the cutoff frequency to be 1 by 2 pi R2C. Now we have to find out what is the R2 value. So the cutoff frequency value is given to be 5 kHz. This capacitance value is given to be 10 nanofarad. So you can easily find out what is the value of R2 from this expression. That is R2 is equal to 1 by 2 pi LC. So simply we will put all these value and we can get the R2 value to be 3.14 kilo ohm. So that is the solution for question number 13. Thank you. Next question is question number 37. In this question, basically a voltage series feedback regulator is given. Okay, that is there is a transistor, an op-amp, and a Zener diode. So we have to find out what is the value of this resistance. Okay, the input unregulated voltage, that is 12 volt, is given. At the output the voltage is 9 volt, and beta value is also given 100, and the Zener breakdown voltage is given to be 4.7 volt. We have to find out what is the value of this resistance. If we see here, the op-amp will be acting as an amplifier, because there will be a negative feedback. So virtual ground concept we can apply. So both are the non-inverting and inverting terminal, the potential will become 4.7 volt. So what are the things given? Op-amp is ideal and there is a negative feedback. As you can see, the transistor will be on, hence there will be negative feedback. So we can apply virtual ground concept, hence V minus, that is non-inverting voltage, and inverting voltage will have the same value, that is 4.7 volt. Okay, so here the voltage is 4.7 volt and here it is 9 volt. Hence we can find out what is the current across this 1 kilo ohm resistor easily. Suppose I1 is the current that is flowing through 1 kilo ohm resistor. As there will be no current flowing through this branch, that is into the inverting terminal or out of the inverting terminal, the current will be 0. So we can write the current flowing through this resistor R is same as the current I1. So I is equal to I1. We can easily find out what is the value of I1. I1 is nothing but 9 minus 4.7 divided by 1K. We can write like this: V minus divided by R, that is the current I, is equal to V0 minus V0 minus V minus divided by the resistance, that is 1K. Okay, so we have all these value. V minus value is known, V0 value is known. We will substitute those things. After substituting, we will get the value of resistance, that is R value is equal to 1093 ohm. As we have to find out the value in ohm only, so we have to write here 1093. So that is the solution for question number 37. Next question is question number 38. In this question, an op-amp circuit is given and it is given that it has finite input impedance, infinite voltage gain, 0 input offset voltage. What will be the output voltage that we have to find out? So if we see, it is given that the gain is infinite, so V0 by VID, that is the input difference voltage, is equal to infinity. That is the gain is gain given to be infinity. Okay, so this can be true only when both V plus and V minus will be at same potential, because the denominator value will be 0, so the gain will become infinity. So if we see here the non-inverting terminal is grounded, so whatever the potential is here, the same potential is also here. So the potential at this point, that is V minus, will be also at 0 potential. So as this is grounded and there is 0 potential, so no current will be flowing through this R1 resistor. Okay, so the same offset current I1 will be flowing through this R2 resistor, as there is no current division is happening through this R1 resistor. Suppose let us name the current through R1 resistor is I and current through R2 resistor is I3. So you can write the KCL at this point. Okay, KCL at this point, that is I1 will be equal to I plus I3. As I said, this current I is equal to 0. Okay, this current I is equal, as I said, this current I is equal to 0. So we can represent directly I1 equal to 0 plus this I3 current is equal to V output minus 0. Okay, V output minus 0 divided by R2, that is V output by R2. So we can easily get the expression for the output voltage. V output is equal to I1 into R2. Hence among the option, if we see option C, that is I1 R2 is the correct answer. Thank you. Next question is question number 39. In this question, we have to find out what is the voltage gain of this amplifier circuit. Okay, here VB value is given 0.7 volt, beta value is given 200 volt, thermal voltage VT value is given 25 millivolt. We have to find out what is the gain of this amplifier. Here if we see, because of this emitter capacitance, for small signal voltage this RE this RE won't affect the small signal gain. This RE won't affect the small signal gain as it will be short circuited, but this RS will affect the gain. So as you know, the gain of a common emitter amplifier with emitter resistance, the gain expression is minus RC by RE plus RE. Okay. So here in this circuit we can write in this way, because this RE expression may create confusion with this RE. So we will take this as RE dash. This RE dash is, so we will take this as RE dash. RE dash value is equal to RS, because this RE won't be appearing in the small signal voltage gain, because it will be bypassed by the emitter capacitance. So this is actually the gain of this circuit. We will try to find out what is the value of this RE, then we can find out what is the gain easily. So as I said, this RS is the on bypass resistance across emitter, so that will reflect, or that will affect the overall gain of the amplifier. So RE is nothing but Vt by IE. Vt is nothing but 25 millivolt. We have to find out what is the IE. IE is nothing but the DC current, DC emitter current. For DC analysis, as you know, this capacitance will be open circuited, input voltage, all these capacitance will be open circuited, so we will have only this circuit. Okay. So looking at this point, we can have the Thevenin equivalent circuit like this: Vth, Rth, and this 10 ohm, that is RS, and RE will be 1 kilo ohm. Like that the circuit will be there. So you can find out the current and voltage accordingly. So Thevenin voltage is nothing but 12 into 11 divided by 11 plus 33. That will give us 3 volt. Okay, Vth is 3 volt and Rth is nothing but the parallel combination of R1 and R2. Okay, Rth is nothing but the parallel combination of R1 and R2. That will give us 8.25 kilo ohm. Okay, so we can find out the IV current, that is the base current, by applying the KVL across this loop. That is IV equal to Vth minus 0.7 divided by the resistance across this, that is Rth plus beta plus 1 RE plus RS. Okay, so accordingly we can find out what is the IV value, and then beta plus 1 times the IV value will give us the emitter current IE, that is 2.21 milliampere, that is 2.211 milliampere. So we got the value of IE, we can substitute here to get the value of RE resistance. So RE resistance value will be 25 by 2.211, that will give us 11.31 ohm. So RE value we got 11.31 ohm. Now the gain will be minus 5k, that is RC value is 5k divided by 11.31 plus RE dash. RE dash is nothing but RS, that is 10. Okay, so after solving this we will get the value of the gain to be minus 234.6, and that is the answer for the question number 39. If we want to find out how this expression came, then we can easily find out from the small signal circuit. We can easily draw the small signal circuit, that is Rth will be here, that is parallel combination of R1 and R2, and beta RE, and here the RS will be there, beta IV, that is the current dependent current source, RC is the only resistance that is here, and all this DC value, all the DC voltage will be 0, or they will be represented by their internal resistance, that is 0. That's why those will be removed and these things will be grounded. So the small signal circuit will be looking like this. So you can find out what is the voltage gain from this small signal circuit. Here the V output voltage is equal to minus beta IV into RC. So the output voltage is minus beta IV into RC. Now we have to find out IV in terms of V1. We will try to find out the expression of IV in terms of V1. So V1 is nothing but IB into beta RE plus both the current will be flowing through RS. We will apply KVL across this loop. So this is the loop. We will apply KVL across this loop. Hence the input voltage will become IB into beta RE plus beta plus 1 because IB plus beta IB, that will give us beta plus 1 IB into RS. So we can easily get this expression. From this expression we can write IB in terms of VI, that is the input voltage. So just the IB value will be equal to VI divided by this factor. Now we can substitute this IB in this expression, then we can find out what is the V output by V input. Okay, so we will substitute this and that will give us the gain value. That is, the gain is nothing but minus beta RC divided by beta RE plus beta plus 1 RS for large beta value. So this is the gain, that is minus beta RC divided by beta RE plus beta plus 1. For large beta value, beta plus 1 will be same as beta. So beta can be cancelled. Hence we can get the gain to be minus RC divided by RE plus RS. That is the same expression for the gain that we have written previously. So if we try to find out the exact value, that is the voltage gain, by putting all these values in this expression, then we will get the exact value of the gain to be minus 234.08, and by approximation we will get this expression. If we substitute here, then we will get the gain to be minus 234.6. So it is very close. The gain value is very close. So that is the solution for question number 39. This concludes analysis of all the questions those were appeared in GATE 2014 set 1 with respect to analog circuit. If any question is missing or any questions are missing, then please let me know so that those questions also can be added in this part. If you have any query or suggestion, please let me know. I am very happy to address your issues. See you in the next lecture. Until then, stay safe, stay healthy, and most importantly, keep preparing harder and harder. Thank you.